Good stuff. I'm going to reach right in front of you and get this. All right, so we're going to start with a little bit of a lab, okay? And we would have usually done this like the whole day. That looks good. The first day is an intro lab, but instead we're going to start with a little introduction demonstration, okay? What we would have normally done is the lab that's on the front page of your packet. This is thermochemistry. That's what we're getting into. And I have what's called perfect data, okay? And I already have that written down, but we have the gentlemen up here that are going to give us a secondary amount and piece of data here. So we're going to start actually writing in trial 2. What we would normally do in this investigative lab is we would talk about hot water and cold water. I know it's not mind-blowing here. Okay, but what we're going to do, we'll start over here. How much hot water and cold water did you put in each one of your cups?
I put 70.
70 milliliters in the hot water and the cold water cup. So I want you to, and I want you to do this in spot 2 since I have my data in spot 1. He got 70 milliliters of hot water and he got 70 milliliters of cold water. Okay. Now what I want you to do is I would like for you to put your thermometer in the hot water one or just one of them. Doesn't matter. How much did you get in each?
75.
75. Beautiful. So 75 and 75. All right. Get the temperature of one of yours, hot or cold. Doesn't matter. What are we looking at here? Is this the hot one? Well, that's still going up. Hot water. What we're going to do is we're going to mix hot water and cold water together. You guys can probably guess what is going to happen. All right. What are we looking at? 48.8. All right, so the 70 mils hot is 48.8 degrees. How about your hot?
48.1.
Ooh, 48.1. Get your cold now. Oh, I didn't even stop my music. Fun. All right, now we're going to get the cold water temp. It's going down. It's going down. Good stuff. Oh, yeah. Now, I did have ice water that we were cooling down for them up here. Once it kind of levels off. Oh, now it's jumping back up. How about we read that? Oh. We'll call that 9.4 for the cold for the 70. And how about you over here?
12.3.
12.3. All right, what you guys are going to do is you're going to mix your hot and cold water. And then I want you to see what temperature it will settle on. Okay, ready, go. Doesn't matter. It doesn't. Yeah. Stir it with the thermometer. Stir it with the thermometer. And let's see what temperature it might settle on. Now, those of you watching, do you think it's going to be above the hot, below the cold? What do you think when you mix hot and cold water together? Not a brain buster here, but we can kind of talk. It's going to lead us into some conversation. 28.0 on you. And for you?
29.3.
29.3. All right, thank you so much. I'll leave this up here so you guys can write this data down. Thank you guys for helping me. Let's see. Oh, if everybody's at home, I have 2 people watching at home. Hey, will you guys go to Baychem 2? You guys over here. Nothing. Oh, Baychem 2. There, that might take you. Oh, yay. Oh, yay. All right, so I changed my thing. They say that the rooms expire after 90 days. So Baychem 2, whenever you guys call, if you're going to be out, Baychem 2 is where you're going to go. Okay? Second quarter, Baychem 2. But I logged on just in case anybody forgot. And then went in Baychem 1. Perfect. All right, then in a perfect world with perfect data, if I would have done it, obviously, because I have perfect data, just kidding. If we had 50 milliliters, and let's say my temperature was 58 degrees for my hot, and 50 milliliters, and my temperature was 22 degrees, we would say maybe it met at 40. All right, so this is the investigative lab you would have done before we started any lecture or anything about thermochem. You guys have all had experiences with hot and cold water, and when you mix them together, I'm sure none of you are blown away about the results and things like that. But let's use some of this data to drive some of our lecture today, okay? So here we go. What I would do on the second day after you've mixed some water and did some post-lab questions, I would ask you to do a math problem. So what we would do is we would take our hot and take the difference from our hot and our mixed. And there's a little triangle at the bottom because I'm going to start using this term a lot. The triangle in science is a Greek triangle. It's called delta. And delta simply means to change. So I believe you have that little triangle at the bottom on your worksheet here. So what I want to find out is the delta of the hot water and the delta of the cold water. Okay, so we're going to do mine first. So my hot water started at 58 degrees, and then the mixed temperature ended up being 40. So what was my delta T, or temperature change, of my hot water? It went from 58 to 40, which was 18 degrees Celsius. My cold, in a perfect world, went from 22 to 40, and so that was a change of 18 degrees Celsius. So let's have somebody grab a calculator. Let's do the delta T's for the gentleman's experiment up here. Now, please note that they use the exact same amount of water. That is very important. We can talk about that later about intensive and extensive, but it's the exact same amount of water. So the first one here, we have 48.8, and we went to 28.0. And then our cold went from 9.4 to 28.0. So let's just check the difference. Oh, oops. Don't let me put that there. Don't let me write this wrong. Cold, 9.4 to 28.0. All right. So the delta T for our hot water here was 20. Well, that was easy. Why did I do that again? 0.8. And my delta T here was 18.6. Okay, so they each changed some temperature. Let's check the next one. 48.1. Oh, I will write them down for you. So we started at 48.1 degrees, and we met at 29.3. And then my cold started at 12.3, and it met at 29.3. All right, so my delta T of my hot, it went from 48 to 29.3. That was going to give me 18.8. And this was a delta T of 17 degrees. Okay. So after you would have done all that, we would now be taking a look at these numbers in the middle. Does it surprise anybody that the hot water cooled down and the cold water warmed up? Doesn't surprise you that they met somewhere in the middle. In a perfect world, and I had these guys rushed here, and you would have done 5 trials if it had been regular, kind of in a perfect world over here, what you guys should have been hopefully seeing is that you started at a number, and then they should have met in the middle, okay? And so what hopefully we would have seen is that the amount of energy gained by the cold water should have been exactly equal to the amount of energy lost by the hot. And they were very, very close. You were within 2 degrees, okay? So this big idea when we're transferring energy is that energy gained by or lost by something is equal to energy gained by something else. So you would have walked away with this from this lab thinking the hot water lost energy into the cold water, which gained energy. Okay. So when we're talking about energy, we're talking about the speed of the particles, all that kind of good stuff. So we're about to get in and formally lecture that. But I think it didn't hurt to come in with a little bit of lab data to kind of show you and jog your memory and talk about what we are going to talk about today. Okay? Awesome. So albeit boring, that's the lab that you kind of would have done here. So wherever you're keeping your notes, let's get our notes on out here. Get your notes on out here. Thermal Chem notes number 1. I hope everybody had a good weekend. Yes. And it's a rainy Monday. So we're missing. Oh, this doesn't say anybody's names on here. There it is. All right. All right. I think that's the only person we're missing. All right, let's do this. All right, so the first thing we're going to talk about today is we are going to talk about the energy of things around us. So the first thing, let's just jot down very quickly, is the word kinetic energy. Kinetic energy. You guys probably know about kinetic energy. Kinetic energy is the energy of what? Movement. Very good. Okay, energy of particle movement. So we aren't talking about big moving things, while usually you guys would be talking about, in physics, you're talking about big moving things. We are talking about small moving things. Okay, so when I'm talking about movement in a substance, I am talking about the actual particles moving. Okay, take your hand, put it on your desk. Can you feel the particles moving? No, you cannot. Okay, but can you feel the addition or the removal of energy from your hand? Yes. So you're feeling the energy change. You just can't feel every single particle. If I were to touch this ice water up here, okay, do you think the particles are moving faster or slower in ice water? They're moving slower at lower temperatures. And in the hot water, they're moving faster. Very good. Okay, so if they're moving faster, that means that they have more energy, and that's usually a higher temp. And we'll get into that in a second. We'll get into that in a second. All right. So we have to break down 3 major terms today, and I can guarantee you that these are going to be in your lecture questions. We're going to talk about thermal energy, we're going to talk about temperature, and we're going to talk about heat. Okay, thermal energy, temperature, and heat. So the first one let's get into is thermal energy. Thermal energy. Thermal energy has one big particular word in it that you need to make sure you're taking a look at. It's where everybody gets confused. Thermal energy is the total kinetic energy of the particles in a substance. So mass does matter. The total kinetic energy of all the particles. We are going to spend a lot of time calculating this later next week. You're going to learn QMC delta T. And we're going to talk about Q a lot as thermal energy. The total kinetic energy of all the particles in a substance. Okay, so mass is important in thermal energy. The unit for thermal energy is called a joule. And it's Joule because it's based on the person that found it. It's their last name, not like a gemstone. But joules, or you will write the unit as a capital J. So thermal energy are joules, okay? And if you would care to know, I want to jot it down, now that you know these terms, thermal energy is extensive. Thermal energy is extensive. So what that means is that mass does count. On the pre-test that I gave the students that were in school last week, and it was just something after the test to keep them busy, we talked about which would have more energy. A 100,000 liter iceberg at 0 degrees Celsius, or like 0.5 liter cup of hot coffee at 100 degrees Celsius. Which would have more thermal energy? What do you think? Okay, it's at a higher temperature. Okay, but if you're looking at it, if this is 100,000 liters, I have so many more particles that the one that actually has more thermal energy is that guy here. So it has a higher, more temperature in it. I get that. And the particles are moving faster. Absolutely. But when you look at this idea and what we're going to talk about in the future, Q is equal to MC delta T, it really has to do with mass when you're talking about thermal energy. Okay, so this iceberg here at the end of the day has more thermal energy. Okay, so thermal energy is one thing, and we're going to talk about that. This is kind of a day to get everybody on the same page here. I do want to spend just a moment because I believe that this is in your middle school standards. I know they teach it in physical science, but probably a lot of you haven't taken it. There are 3 ways that energy moves, and we are just going to define this and move on to make sure if I talk about conduction, you know what I'm saying. So there's conduction, convection, and radiation. Have you guys heard of these terms before? Yes. Conduction is when you touch something. Convection is when it moves in a liquid or a gas. And radiation is when it moves without particles. So I'm going to break this down real fast. Okay. Again, this is just a recap. Usually the first lecture of any of our new units is making sure everybody's on the same page. Conduction, you have to have particle to particle touching. That's how, if I pick up this cold beaker of water and I put my hand on it, woo, okay, I feel some joules being removed from my hand. In conduction, it has to be touching. Convection is when a liquid or a gas will move, okay? It's a transfer of energy, a liquid or gas. It's a movement by a current. So it's how weather is driven. It's how the currents in the ocean or rivers move around, things like that. But you have to have a moving form of matter. You guys probably, when you learned about this, when you were first learning about it, you talked about boiling macaroni and cheese. You know how it goes up and down and up and down and up and down and stuff like that. Okay. Convection is also how your hot air balloons work, things like that. So it's a movement by currents. And radiation is energy that does not need particles. Energy that moves as electromagnetic waves. Okay, so that is a lot really fast at you. We almost took the slide out completely because we don't use a lot of it. But if I use this term conduction or convection, I want you to be able to know, kind of make sure everybody's on the same page with that. Perfect. Okay, so that was a lot. Just going to take a moment. And again, if you want to just write the red, just to remind yourself kind of these terms. But I'm almost sure that these were in the middle school standards. Okay. Awesome. And if you have any questions on this, the worksheet that I gave you does have a little more practice with this. I'm just not going to spend any more time on it. Okay. All right. So next, we have what's called the law of conservation of energy. You guys already learned about the law of conservation of mass, and this is no different. Okay. When I mix my hot and my cold water together, where did the energy from the hot water go? And where did the energy that warmed the cold water come from? They came from each other, right? The hot water's energy went into the cold water to warm it up. And because it lost energy, it cooled down. So they met in the middle. Energy can't just come from anywhere. You can't make energy. You can't destroy energy. So it is called the law of conservation of energy. Energy also cannot be created or destroyed. If you gained energy from anywhere, or if you gained energy at all, it had to have come from somewhere. This is going to be huge in some of our math coming up. Some of everybody's favorite math has to do with the law of conservation of energy. Don't forget your law of conservation mass. Don't think you have to write it down, but just keep it in the back of your head. Mass and energy have to be conserved. So if something heats up, that energy had to come from somewhere. And if something cools down, that energy had to have come from somewhere too. Or go somewhere, I should say. Okay? Energy cannot be created or destroyed. If you heat up, that came from somewhere. If it cools down, it has to go somewhere. Perfect. All right, all right. A little bit more. Now, don't write this slide down. I'm just prompting you for this conversation about temperature. We said that thermal energy was the total amount of energy of all the particles in the substance. If I want to take the temperature of this, though, and I put this thermometer in here, does this thermometer have any idea of how much water it is in? It has no idea. So what this thermometer is doing is it's just taking an average. Now let's think about this. How does a thermometer work? If I put it into something hot, do you think the particles are hitting it fast or slow? If it's in something hot, the particles are hitting it very quickly. Okay, so the temperature goes up. If I put it into something cold, are the particles hitting it faster or slower? Slower, so the temperature will go down. Very good. So as we're talking about, okay, the difference between thermal energy, we said, is the total. Temperature happens to be the average kinetic energy of the particles in a substance. And again, this is the important term here. You can bet your bottom dollar I put this in the lecture questions as well. Mass does not matter in temperature because it's just an average. This thermometer is doing its best to figure out the temperature of that water. And what it measures is how quickly particles are hitting it. It doesn't know how many particles are hitting it. It just tries to figure out how fast. Okay? The unit is degrees Celsius, or there's a new unit we'll be talking about in this class, which is called Kelvin. Kelvin is a scale that reaches absolute zero, and so we'll go further into that later. But again, it's an average. Kelvin is when you take Celsius and you add 273 in order to get that. We'll talk about that more when you need that. But the interesting thing is that temperature is intensive. Remember, that means it does not change with size or amount. I swear I can hear those chickens everywhere. Barring the ice cubes, because those are going to change my conversation here. Let's figure out the temperature of this ice water. All right. We're looking at 8.4 degrees in my ice water here. Okay. I'm going to take this and I'm going to pour some of it out. You think the temperature is going to change? No. How about if I pour out a little bit more? Is the temperature going to change? No. So temperature does not depend on amount. It is an intensive property. Side conversation, don't write any of this down. Just a sidebar. Speaking about this Kelvin thing, Kelvin, like I said, takes into account this absolute zero idea. Absolute zero is when particles are so cold that they actually stop moving. Okay, and we can spend more time on that a little bit later, not for this lecture. If you care, some students get a little confused with Celsius and Fahrenheit and things like that. We usually run in the Fahrenheit world. Okay, water at Fahrenheit freezes at 32 and boils at 212. Okay, that's the numbers you're probably used to seeing. You're like, yay, snow day. Well, snow days are gone, but that's okay. All right, Celsius is where we're going to work here. So if I ask you, and pretty much everything's going to hone around this, water freezes and melts at 0 on the Celsius scale, and it boils at 100. That is something you kind of just need to know. Hopefully you do, probably, and all that kind of good stuff. And then the Kelvin scale is just 273 degrees above that. Okay, so sometimes people just like a frame of reference, but what we're working in with this class is we're working on the Celsius scale. Okay, awesome. All right, so good. We have 2 more things. Heat. Heat is a little bit different than thermal energy and temperature. People want heat to just mean hot things, and that's not necessarily true. Usually when you're experiencing heat, you are experiencing hot things, but heat is defined as the transfer of energy. So thermal energy is the total amount of energy, temperature is the average, and heat is actually the transfer of thermal energy. Okay, awesome. The unit is either calories or joules. We notoriously do a lab in this unit where we burn a lot of snack foods and try to figure out how many calories are in those foods. We'll see what we can do this year. I don't know. Okay, that's a really loud chicken. You hear that thing, right? I'm not like losing my cookies. Is that from all the way around the corner? Must be, but she's like so far, that must be so loud in the room. All right, so heat. Let's talk about if it's intensive or extensive. You know, back when football was played without all these restrictions, at the end of the game, like the Super Bowl, okay, what do they do with the coach? They get this thing of Gatorade, right? And what do they do with it? They dump it on his head, right? To create some thermal exchanges, shall we? What if instead of taking the giant thing of the Gatorade, they're like, guys, I got this. And they got a little pipette, okay? And they're like, I'm going to get him. And they go, with some ice water. Would that do anything to the coach? He's like, what? Get out of here. Why do you think they choose the biggest gallon Gatorade with ice and all that stuff in there? Is so that they can transfer the maximum amount of thermal energy, right? So heat is very much dependent on mass, okay? So it is an extensive thing. If you accidentally splash a little boiling water on your hand, you're like, oh, ouchies, and that's fine. If you were to dunk your hand into some boiling water, now we have problems, okay? So heat, or the transfer of energy, is all about mass, okay? You're not getting anybody with some ice water. You're like, hey, coach, whew, you know, I got you. That doesn't work. Okay, awesome. 2 terms that I want you to know, and I think you do. Conductor and insulator. Again, I'm not trying to insult your intelligence that you don't know these things, but just making sure that we're all on the same page. A conductor easily transfers energy, and we're going to practice with these terms later. And an insulator resists transferring energy. So again, if you want to just write down conductor and insulator because you know it, write it down, or you want to define it, it's up to you. But why did I give them styrofoam cups up here to do this lab? When you guys would have done this, I wouldn't give it to you in glass. I wouldn't give you metal cups. You have styrofoam because it's a insulator, right? It's slowly. So you put your hot coffee in here so it slowly loses its heat energy. It doesn't just cool down very quickly. Okay, so I don't think we need to talk a lot about these. I think you guys know these, but if you have questions, these will be some common terms that we have going on. Okay, last idea before I turn you out to practice some of this stuff. Here we go. Nature's tendency, and this is where people just, for some reason, want to lose their minds, and it's okay. This is one of the things that is very confusing to students, and it's okay. It seems simple, but once you start drawing your heat diagrams, it's going to be a problem. Everything in nature tends to go from high to low, and thermal energy is no different. Heat goes from an area of high temperature to an area of low. So if you really don't feel like writing a lot, you write hot goes to, and I hate this word cold. It's not my thing. Cold really isn't a thing. Okay. You don't go outside on a day like today and get attacked by cold, right? Cold isn't like pressing down on you. What cold is the description of a feeling of when you are losing thermal energy. Okay. Because nothing goes, cold doesn't come onto you. It's a removal of heat. So let's finish this slide. You always speak in a direction of heat. High goes to something, which direction? Coldness does not exist. And what we're going to do to show me that you guys understand this stuff is we're going to do what are called heat diagrams. Okay, so what I want you to do right now, you can probably play at home too, if you have metal near you. What I want you to do is I want you to take one hand and I want you to put it on the wooden part of your desk. Like, yeah. Oh, okay. That's nice. And I want you to take the other hand and I want you to grab the metal part of your chair leg. Oh, do those feel like they're at two different temperatures? They do, right? But they've been sitting in this room for the whole weekend. I promise I haven't gone around and like warmed anything up. So is the table and the chair at a different temperature? No, they're at room temperature, right? They're all at the same temperature. So why does one feel one way and the other feel the other way? And we're going back here. Talk to me. Talk to me. The metal chair is a conductor and the table itself is an insulator. Wood is an insulator. So not that you have to write this down because we're just talking about it. The metal chair probably felt cold, okay? And the table probably felt a little bit warmer. However, they're both at the same temperature. So what you have is because metal is a conductor. So what you would do, okay? Oh, and I apparently left my thing up from last year, okay? In a heat energy diagram, and these sometimes tend to be cold, or hard, you got to draw which direction heat is. So this is you. Again, I was going to be an art student. I mean, whoop, there you are. You're looking good. Okay. You are pretty warm. Okay. You're about 36 degrees Celsius, let's say. And the room, let's say it's about 23 degrees Celsius. Oh, I have it. You're 37. You must be feeling chilly today. But that means that the table is at 23 degrees Celsius and the chair is at 23 degrees Celsius. When you do a heat diagram, you want to put where the high energy and where the low energy is and show me the direction of transfer. You are the high thermal energy and the temperature of the chair is low compared to you and the table is low compared to you. So when you touch the table, energy goes from you to the table, and when you touch the chair, it goes from you to the chair. Coldness is not a thing. Cold is not being applied to your body. Cold is when you have energy being removed from yourself, okay? When you go outside, you feel cold because all of a sudden the air around you is like, oh, take that heat, okay? Because everything goes from high to low. So you will have to do a lot of these energy diagrams. We can do a couple right now to practice. Oh, and then there's this cool little fun thing. Speaking of conduction, convection, and radiation, if you have, and this is something you guys can do at home, and it works best with like the nicer tea. I bought a box of the kind of little cheap tea, and it didn't really work. I think it's a little too heavy. But so you take some tea. This is good and expired, so we're not sacrilege you tea drinkers. And what we're going to do here is it's actually a tube, if you didn't know. So I'm going to take, and those of you at home, I'm taking the tea and I'm just going to dump it out. Has anybody seen this before? The tea bag demonstration. So I have a cylinder, okay? And it just is the outside the stuff that holds the tea here. And what I'm going to do is I'm going to place it right here. Hopefully you can see that at home. Yep. And so that's just the inside or the outside of the tea in which you would steep it. Okay. We said that convection is when you have a movement of air or a liquid. So I have this here and I'm just going to heat it to the top, and everybody's like, that's lame for the first 30 seconds, and then your socks are going to get knocked off. Ready? Socks. Knocked off. So what happened was you heat up that air inside. It's like a little hot air balloon. You heat the air inside of the little tea bag, and then it will warm, and then convection goes up as it cools, then it falls back down. Okay, so I don't know if you want to impress your friends. Oh, I hope it was going to land back on the table. Makes a little bit of a mess, so make sure you're ready to clean it up. So that is some convection. Okay, good stuff. So the last thing I want you guys to do here is there is a little worksheet, okay, on the next page of your packet. I have the key online. So there are a lot of examples of thermal energy in your everyday life, okay? In the morning, you walk into your bathroom with your eyes half open and you step on the tile. The tile feels, for lack of a better word, cold, correct? What do you then choose to step on in your bathroom that will make your feet not feel cold? You step onto the rug, right? So the first thing here is, why does your bath mat or your rug feel warmer than the tile floor? So you're going to have to write a little bit, but I also want to help you do your heat diagram first. We said you're about 36 or 37 degrees Celsius. And your room, if it's particularly cold, let's say maybe it's 22 degrees Celsius, are both things in your room the exact same temperature on the floor? Unless you have some like heated floors, which I'm jealous, they're both the same temperature, correct? So let's do a high to low energy diagram. Your foot on the tile, is your foot hotter or cooler than the tile? Hotter. And your foot, the tile is lower. So which direction is energy flowing? It's flowing from you into the tile. Same thing. You're higher when you're on your rug, and the rug is lower. So which direction is energy? It always goes from high to low. So that's your energy diagram that you have to be able to draw. Now, riddle me this. Why does the tile feel colder to you, though, than the rug? Talk to me.
Tiles are a conductor.
Wonderful. So while they are both taking thermal energy from you, the tile is a conductor. So it goes, give me that energy now. And it steals all your energy. Okay. While the rug is like, I want that energy. And it goes like really slow and it can't really get it. Okay. Things like that. So one will quickly transfer energy away from you, and one will slowly transfer energy away from you. But what people want to say wrong is they're like, oh, well, one gives you energy and one takes your energy. No, they both are trying to remove your energy. One's just more efficient at it than the other. Okay. And then there's little conduction, convection, radiation practice. And then there's another scenario. So these scenarios, this test normally is quite challenging. And we will give you a lot of these thinkers and make you write. I'm not quite sure how that's going to work on Schoology, but I would be prepared to answer questions like this, okay? We might just break down and have you type in some answers at this point, because some of these things can only be best explained by you to show me that you understand. Okay, conduction, convection, radiation. If you get a sunburn, that comes from the sun, where the energy moves through outer space, and space is called space because there's nothing in it. So that has to be the one that doesn't need particles. Hot air balloon kind of looks like this. Cooking eggs, touching a metal pan. So this is practicing conduction, convection, radiation to see if you have any issues with that. And then how does styrofoam keep things cold? So do me a heat diagram. If you have ice cream versus air temperature, which is high, which is low, all that kind of good stuff. And the key is online. And if you want to open up your Chromebooks, you have about 2 minutes now. I didn't realize. If you want to do the lecture questions, those of you at home, hit up those lecture questions. I would keep your notes out. Guarantee you that those notes will help you on your lecture questions. But I'll give you the remainder of the period here to hit up those lecture questions and finish this worksheet. Oh, and I didn't take attendance of people at home. I'm going to yell.